Okay, howdy science bowlers. This is my quickie science bowl version of kinematics, Newton's laws, circular and rotational motion. So, you probably know these two guys. And actually this one's probably good too. Okay. So, these are kinematic equations. You know what? I'm going to write down the fourth one too. We'll talk about them all. Okay. So kinematic equations are only good for something that has a constant acceleration. So all the guys, so this is V naught, this is the initial velocity. There's all the initial velocities. The V with no subscript is a final velocity. T is the time that it's taking. Delta X is the displacement, that's X final minus X initial. And then this is average velocity. We'll talk more about that in a little bit. To make your life easier to make it doable in 20 seconds, often your objects are starting at rest. And these are the most useful equations for you. So when it's at rest, after a time t, it has an acceleration a, it's got that velocity. So you know that, right? So with free fall, where g is 10 meters per second squared, right? Every second, the speed increases, or changes, I should say, by 10 meters per second. This one, d equals 1/2 at squared. This is the distance after a time t accelerating, and this is from rest as well. So, with free fall, right? Free fall is when gravity is the only force acting on it. So g is 10 meters per second squared. I'm used to using 10 meters per second squared. Obviously, Science Bowl sometimes wants you to use 9.8. But here's a very useful fact, actually, that I saw them assume that you know. After 1 second, it falls 5 meters. After 2 seconds, it's 20. After 3 seconds, it falls 45 meters. When you do d equals 1/2 gt squared, right, it's basically 1/2 of 10, so it's 5t squared. So 5t squared, 5t squared, 5t squared. I saw one of the questions that they asked you gave you a g of 5 meters per second squared and asked you how far it fell after 2 seconds, right? And so it was, or I think actually it was a different problem, whatever, doesn't matter. But the point is that if you happen to just have this 1/2 gt squared, if you do this enough, those numbers will actually be in your head. The other thing about free fall is in projectile motion, right? All projectile motion is it is a free fall problem in the y direction, right? Because you've got g down, and a constant velocity problem in the x direction. Trying to think of the kinds of problems they've asked you. The time that it takes to get to the top here is just this problem, right? Do you see that? That's just, there's a glorious symmetry with projectile motion. As long as there's no air resistance, they're not going to give you air resistance on that, unless they say something like, oh, if it's air resistance, then it would land closer or something. But yeah, so hopefully that clears something up there. All right. In general, acceleration is a change in velocity over time, right? When A and V are in the same direction, or they have the same sign, it's speeding up. When acceleration and velocity are in opposite directions, it's slowing down. I did see a problem basically asking exactly that. Constant velocity. All right, what is constant velocity. Velocity is a vector. Velocity is a speed in a certain direction, right? So constant velocity means not just a constant speed, but also a constant direction, otherwise known as a straight line. Cool, that's useful. What does that mean also? Constant velocity, if it's a constant velocity, then there's no change in velocity. So constant velocity means the acceleration is 0, and the net force has to also be 0 because of Newton's second law. Boop. Okay. Should we talk about Newton's laws? I don't want this to be a 20-minute video, so I'm trying to just go quickly. First is the law of inertia. This is the thing that says, you know, things want to just keep doing what they're doing. Second is your equation, and really intuitively, you should think about it more like this. Acceleration is caused by a net force, and the bigger the mass, the less that net force is going to give, the less acceleration that net force is going to give you. And the third is your action reaction, right? That's the idea that, you know, a bug hits, wow, this is an amazing picture. That's a car, and that's your windshield. A bug hits your windshield, right? Which feels a bigger force. They both feel the same force. They're part of the same interaction. It's just that the bug feels a bigger acceleration, right? So they have the same net force, but you have a bigger acceleration because of the smaller mass. Another thing is when you drop an apple, right? You've got the force on the apple by the earth. The force on the earth by the apple is the exact same amount. It's just that the earth has a big honking mass, and so negligible acceleration. Groovy. All right, I saw a problem. I don't remember how it was worded. Sorry, I didn't write it down. But basically, it asked, you know, you're pulling this thing. So you have this applied force, and then you have some frictional force. And it asked you how much force to keep this thing going at a constant velocity. Okay, constant velocity screams acceleration is 0, which screams net force equals 0. So in this case, right, the applied force is equal to that friction force. You might also remember that, like, if it's just on this horizontal thing, then Fn is mg, and then friction is fun. Sorry. It's people say friction is fun because they write normal force with an N. Often I just do this. Oh my gosh. Sorry. I'm not starting this video over though. You're just going to watch me screw up. Okay. That's friction. That's the force of, this is going to be kinetic friction in this case. And that's the coefficient of kinetic friction, and that's the normal force. In this case, the normal force is mg. So mu mg comes up a lot. So you'll see that. What about if it's on an inclined plane? So this is super common. They might just expect you to know these components. Let me grab another color. All right, so if this is at an inclined theta, that's your theta. The component going down the plane, causing your acceleration this way, is mg sine theta. And in this case, your normal force is mg cosine theta. For those of you who are about to be in my class, you're going to see this a lot. All right. That was fun. Ooh, all right. Halfway there. Other words that come up with velocity, and I did promise I would get back to you on this, was instantaneous. Velocity versus average velocity, so that was one of your kinematic equations, versus average speed. These, especially the average velocity and average speed, are tricky. Instantaneous velocities, that velocity in your kinematic equations. Those are the ones that you're used to doing calculations with. Average velocity is the displacement over time. Remember, displacement is a vector. It's the final position minus the initial position. The average speed is a scalar, and it's the total distance over time. That fourth kinematic equation, where it was v plus v naught over 2, that's only for constant acceleration. Okay, but these, my AP kids mess these up all the time. So displacement is a vector. It's final position minus initial position, and that gives you average velocity. Average speed, you get the total distance traveled. All right, that's fun. Uniform circular motion. Okay. So this is where it would be nice if you could actually watch me twirl something, but imagine I'm twirling something. Okay, so the question is, why does something go in a circle? Well, Newton's first law says things don't want to go in circles. They want to just keep doing what they're doing, right? So if you've got this thing, maybe on a string, right, moving around, if I let go right here, it would go whee, right? Because it wants to just keep doing that. The only reason this thing goes in a circle is because this string, let's get a different color, this string or whatever it is pulling it in, okay? So this thing says, I want to go this way. And the string says, no, you're coming with me. I want to go this way. No, you're coming with me. And that's how things go in a circle, okay? So the net, so if it is changing, okay, let's try that again. My bad. Blah, 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 blah. All right. This thing is moving with a speed v here. A time later, it's moving with a speed v here, okay? Sorry. These can be the same v, and with uniform circular motion, it is. It's constant speed, but that direction's changing, right? So it is accelerating because direction changes. So that's a special kind of acceleration. That's not just easily calculable with delta v over delta t. Okay, this is centripetal acceleration. Looking at the word, that's obviously center. Petal is seeking, so it's center seeking because the acceleration, that's a sub c, the acceleration is always towards the center. Okay, center seeking. There's a similar word that you probably know, so let's just get it out of the way. Centrifugal, which is center fleeing. This is a fictitious force that you see in rotating reference frames. Okay, this is center fleeing. This is why when you're driving and you take a turn and it feels like you are thrown out from the center, right? It feels like you're thrown away from the center, fleeing. You're not. It's just that you're going straight and your car hits you. Your car comes and pushes you in with a normal force like that. So this is a fictitious force. It is not a free body diagram kind of force, okay? So centripetal acceleration is caused by, right? Accelerations are caused by forces, and the force that causes the centripetal acceleration is called the centripetal force. But be careful. This is not a just magical force. This is some combination of, tensions, weight, sometimes when you've got orbits, it's gravity, Well, actually, that's mg, but it's a different kind of mg. So this centripetal force is whatever the net force is towards the center. Okay? And let's show you what the form of that is. So centripetal acceleration is v squared over r. Okay? So this is that constant speed that it's going, and then that's the radius of the circle. Newton's second law says that, so if we add up all the forces in the centripetal direction, which is like the radial direction, you'll see a sub z or a sub r. The centripetal force, right, is equal to mv squared over r. And there was an interesting problem that I read about, it was a satellite, and, it was at a certain orbital radius r, and it had a certain kinetic energy, right? So this is what they said, is it moves to like a bigger r, let's say 4r, so you made it go to a bigger orbital radius, and the kinetic energy was reduced by a quarter. And then they asked how the centripetal force changed. Okay, so the trick here was to realize that kinetic energy, which is 1/2 mv squared, well, gosh, that mv squared and that mv squared look awfully similar. They're just a factor of a half different. So they were looking for, the centripetal force was mv squared over r. So this thing went by a quarter, this thing was a fourth. So the centripetal force went down by a factor of 16. So that was what was happening there. Okay, so I know I just said I didn't want to make this a 20-minute video, but look at me. I'm almost there. Okay, we're almost done now. All right. In general, rotational motion okay, you've got this thing rotating with an angular velocity omega that's measured in radians per second. So an object here is going to have a certain velocity, and an object here would have a different velocity. That's called the tangential velocity. The tangential velocity is that omega times how far away it is from that center. Okay? I saw one question that called this surface velocity, which is weird to me. I've never heard that, but that's apparently what they mean here. The distance that it sweeps out is whatever theta times r, and the acceleration, the tangential acceleration, this is the angular acceleration times r. So there's a nice like Greek letter times r. So these Greek ones are the rotational variables. The Greek letter times r is the Roman letter. So that's a nice handy dandy thing. Okay, last thing, moment of inertia. So moment of inertia. This is the rotational equivalent of mass. This tells you how hard it is to rotate something. So if you take a meter stick and you try to rotate it from the end, it's going to be a lot harder to rotate than if you try to rotate it from the middle. Okay? And so there are these values that tell you, right? So it's 1/12 ml squared for the center, and it's 1/3 ml squared, right? So obviously that's bigger when you rotate it here. Spheres are 2/5 mr squared. So I wouldn't have necessarily, like for my AP kids, you don't memorize these, right? That's not a thing. But for Science Bowl, they actually expected you to know 2/5 mr squared for a problem I saw. Cylinders and discs are 1/2 mr squared, and hoops are mr squared. So this should make sense to you. A hoop is as far away from the center axis as you can get, and the further away that mass is distributed, the harder it is to rotate. A sphere is as compact as you get, so 2/5 I'm pretty sure is the smallest fraction that you get, because this is a solid sphere, I should say. Hollow spheres have another number that I don't remember actually. But the further away you get, the harder it is to rotate. And last thing, this is Newton's second law for rotation. It looks like this. Remember, A is angular acceleration, m is moment of inertia, and then this is the sum of the torques, right? So the torque causes angular acceleration and is impeded by that moment of inertia. All right, hope that helps, guys.